Okay, let's start with a question. Imagine you are a pilot, Boeing 747, 400 people behind you, you're flying across the Atlantic at night, 30,000 feet, cruising at 500 miles an hour. And then the entire instrument panel goes dark. No altimeter, no airspeed indicator, no fuel gauge, no engine temperature, just black glass in every direction. What do you do? Here's the thing. You might feel fine, the engines still sound okay, the plane doesn't feel like it's falling, but feeling fine is not information. For all you know, you're slowly losing altitude. For all you know, one engine is running hot. For all you know, you've drifted off course and there's a mountain range coming up in 12 minutes. The feeling of stability is not the same as actual stability, and that gap between how things feel and what's actually happening is exactly where planes go down. This is how most developers run production software. We spend weeks building this complex, distributed thing, caches, queues, microservices, database shards, and then we deploy it to the cloud, see a green light on AWS, and assume everything is working. We're flying blind, and we won't know until something goes wrong. So today, we're going to talk about observability, what it actually is, why it's not the same as monitoring, and how you think about it from first principles, starting from what a system fundamentally needs to be knowable from the outside. Let's start at the bottom. First, let's get the vocabulary right, because people use monitoring and observability interchangeably, and they're not the same thing. Monitoring is reactive. It tells you something is wrong. An alert fires. A dashboard turns red. Your phone buzzes at 3 a.m. The system is sick. Observability is something different. It's the ability to understand the internal state of a system by looking at its external outputs. When something goes wrong, observability is what lets you actually figure out why, without having to redeploy code or SSH into a server and poke around. Here's an analogy that makes this concrete. Monitoring is the fire alarm. Observability is the ability to walk into a building, see where the smoke is coming from, which wall the electrical short is behind, and what started it, without having to knock down walls. This distinction matters a lot in distributed systems. When your monolith crashes, you can usually look at the stack trace and find the problem. But when you have 15 services talking to each other, and one of them is sometimes slow, and that slowness occasionally cascades into timeouts elsewhere, the stack trace doesn't exist. There's no single place to look. You need to be able to reconstruct what happened across multiple independent processes. Observability gives you that reconstruction ability, and it's built from 3 fundamental data types. In SRE, Site Reliability Engineering, we call them the 3 pillars: logs, metrics, and traces. They each answer a different question. Let me explain each one from first principles. Here's how I think about the 3 pillars. Each is a different answer to the question, what do I need to record about my system? Logs are events, discrete things that happened with as much context as you want to attach. User 4821 attempted login at 142307. IP address. Failed. Wrong password. Logs are high cardinality. You can put anything in them, but they're expensive. If you're a large company processing millions of requests per minute, logging every request fully is genuinely costly to store and search. Finding one thing in a trillion log lines is slow. It's like Control F on a document that's a billion pages long. Metrics are aggregations over time, numbers sampled at regular intervals, CPU at 67%, requests per second 1400, error rate 0.3%. Metrics are incredibly cheap. A floating point number takes almost no space. You can store years of metrics in memory, and they're perfect for alerting. You can say, if error rate goes above 1%, wake me up. But metrics have low cardinality. They don't tell you which user failed. They tell you that someone failed. Traces are the journey of a single request through a distributed system. Request arrives at the gateway does the auth service, that takes 8 milliseconds, auth service calls the user database, that takes 12 milliseconds, auth returns, gateway calls the product service, that takes 340 milliseconds, and so on. A trace is a connected timeline for a single transaction spanning multiple processes. Here's the one-liner worth memorizing. Metrics tell you there is a fire. Traces tell you which room. Logs tell you what started it. You need all three. They're not alternatives, they're complements. A good observability stack has all three, and ideally they're connected. You see a metric spike, you pivot to a trace. You pivot to a log line. That's the workflow. Now, how do traces actually work in a system with 15 separate services? This is interesting mechanically. Let me explain it. When a request arrives at your gateway, the gateway does one specific thing before anything else. It generates a random unique string. Something like trace_ID:A3F92C1B. Call it the correlation ID. Every internal service call that gateway makes, it attaches this ID in the request header. Every service that receives that header does two things. It includes the ID in any logs it writes, and it passes the ID along when it calls downstream services. Now, when you want to understand why user 4821 had a slow request, you don't search through 15 different log dashboards. You search for that one ID across all your logs, and suddenly every log line from every service, sorted by timestamp, lines up into a single coherent timeline. Think of it like tagging a parcel. Every stop, the warehouse, the delivery van, the regional hub, scans the tracking number. You can reconstruct the entire journey from a single search. Without the number, you'd have to call each stop and manually piece it together. Without tracing, engineers debugging a distributed system are in different rooms looking at different logs, trying to guess how the events connect. With tracing, there's a single source of truth. The auth service took 9 milliseconds. The product lookup took 11 milliseconds. But the database join inside the product service took 430 milliseconds. That's your problem. That's not a guess. That's a measurement. That's the difference. Okay, now we know how to collect observability data. The next question is, what do you actually watch? If you have 1,000 metrics, you effectively have 0 metrics. The noise drowns the signal. You'll be staring at dashboards and still not know if the system is healthy. Google's SRE team, after years of running some of the world's most complex distributed systems, distilled system health down to 4 signals. They called them the 4 golden signals. And the insight is, if these 4 look good, your system is probably fine. If one looks bad, you have a problem. The first signal is latency. How long does it take to handle a request? But here's the critical detail, and I want to spend a moment on this because it's where a lot of engineers go wrong. The average latency is almost useless. Let me show you why. Suppose you have 100 requests. 99 of them complete in 10 milliseconds. One of them takes 10 seconds. Maybe it's hitting a particularly large record in the database. Your average? About 110 milliseconds. Great, we're fine. But for that one user, your app is effectively broken. And in microservice architectures, if your service is called as part of a chain, one slow response can cascade into downstream timeouts. We don't track averages, we track percentiles. P50, the median, is the middle experience. Half your users are faster than this. P90, 90% of users are faster. This shows you the heavy requests. P99, this is the tail latency. This is the worst 1% of users. This is where the real pain lives. Optimize for P99. Here's why. In a distributed system, if a request has to touch 10 services and each service has a 1% chance of being slow, the probability that the overall request is slow is roughly 10%.
The tail is not a rare edge case, it's a systematic tax on your users. The second signal is traffic. How much load is hitting your system right now? Requests per second, concurrent WebSocket connections, messages queued in Kafka. Traffic is the why. If latency is rising, is it because your code got slower or because traffic tripled? These have completely different solutions. Traffic gives you the context to tell them apart. The third signal is errors. What fraction of requests are failing? Not just HTTP 500s, also implicit failures. A 200 response that returns an empty list when it should have data. A request that completed but took 4 seconds when your SLO says anything over 1 second is a failure. You track error rate as a percentage of total traffic. 0.1% is probably fine. 5% is a crisis. The fourth signal, and the most interesting one, is saturation. How full is your most constrained resource? CPU at what percentage? Memory? Database connections? Disk I/O? Saturation is the most interesting signal because it's a leading indicator. Your P99 latency might still look fine when CPU hits 85%, but at 91%, the OS starts context switching aggressively, caches thrash, and latency doesn't go up linearly, it explodes. Which brings us to the next part. Most people think about resource saturation linearly. If the system handles 1,000 requests per second at 50% CPU, it should handle 2,000 at 100%. This is wrong.
And understanding why it's wrong comes from a field called queuing theory, the mathematics of waiting lines. Imagine a grocery store with one cashier. Customers arrive once every 2 minutes. Checkout takes 1 minute. The cashier is 50% busy. Nobody waits. Everything works fine. Now, increase the arrival rate. One customer every 65 seconds. The cashier is now roughly 92% utilized. But here's the thing. Arrivals are random. Sometimes 2 people show up at once. A queue starts to form. Push it to 99% utilization. The queue doesn't just get longer, it grows without bound. In the math, wait time approaches infinity. In practice, your latency graph looks flat, 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 and then suddenly vertical. The relationship between utilization and wait time comes from something called the utilization law in queuing theory. Wait time grows proportional to rho over 1 minus rho, where rho is your utilization. At 50%, wait time is roughly equal to service time. At 90%, it's 9 times service time. At 99%, it's 99 times. The curve is convex, not linear. And the steepness of that curve near 100% is why your load test that tops out at 80% can completely miss the failure mode that appears at 85. So what does this mean practically? It means you don't alert at 100% saturation, you alert at 70. At 70%, you have runway to act. You can scale horizontally, increase the connection pool, add a cache. By the time you hit 90%, you're already in the exponential regime, and users are feeling it. By 99, you're firefighting. Saturation is your early warning system. Watch it. Alert early. Scale before the math catches up with you. A senior architect knows exactly which resource will hit that limit first. CPU, memory, database connections, disk IOPS, network bandwidth. It's almost never the thing you expect. Now let's move from the technical to the organizational. How do you actually define what healthy means in a way that's unambiguous and doesn't shift depending on who's in the room? SRE gives us a 3-level vocabulary. An SLI, service level indicator, is the raw metric, P99 latency, error rate, availability percentage. It's just a number. An SLO, service level objective, is the target. P99 latency should be below 500 milliseconds. Error rate should be below 0.5%. We should be available 99.9% of the time. This is an internal agreement. It defines success for the engineering team. An SLA, service level agreement, is the customer-facing contract. If we're down more than 4 hours in a month, you get a refund. This is legal. This is commercial. First principle. Your SLO should always be stricter than your SLA. If the SLA says 99.9%, your internal SLO should be 99.95 or better. You want to catch problems before they breach the commercial contract. But the most powerful concept here is the error budget. This is worth really internalizing. If your SLO is 99.9% availability, you are mathematically allowed to be unavailable 0.1% of the time. Over a month, that's about 43 minutes of downtime. That's your budget. If you've had a quiet month and you've used only 5 of those 43 minutes, you have 38 remaining. That's a green light. Ship new features, deploy aggressively, take risks. You have room to absorb a mistake. If you've already burned 40 minutes in the first 2 weeks, you have 3 minutes left. That's a freeze. No new deployments, no experimental features, all hands on reliability until the budget resets. The error budget ends the developers want to move fast versus SREs want stability argument. It's not a philosophical disagreement, it's a math problem. Check the budget. The budget decides. It transforms reliability from a feeling into a resource, one that you spend, save, and account for. 2 final things before we close this out. 1 technical, 1 cultural. And honestly, the cultural one might be the more important of the 2.
The technical one first. Your dashboard should tell you one thing when something breaks: what is broken and what is the impact. I've seen companies with enormous, beautiful dashboards, 60-inch TV screens, 100 spinning gauges, flashing numbers everywhere. It looks like NASA mission control. It's almost completely useless in an actual incident. At 3 in the morning, when your phone wakes you up, you don't want to interpret 100 metrics. You want a top-level signal, the 4 golden signals. You want a mid-level component view, which service is failing, and a debug layer underneath, the actual traces and log lines for the failing requests. Every metric on your dashboard should have a clear action attached to it. If a number turns red and you don't know exactly what you do in response, remove it. It's noise. It dilutes the signal of the metrics that actually matter. Now, the cultural one. Systems fail because of chains of events, not because of one person's mistake. A developer writes a bad query, sure, but why did code review miss it? Why did the staging environment not catch it? Why didn't the circuit breaker trip? Why was the alert threshold set wrong? The failure is a system failure, not a human failure. If you punish people for mistakes, they hide mistakes. They stop logging errors. They stop being honest in incident reports. They stop admitting uncertainty. And in a distributed system, built on the assumption that you can see what's happening, if people stop being transparent, you lose observability entirely. The whole foundation falls apart. The SRE culture is this: every incident is free information about a weakness in your architecture. Document the root cause, create action items, make it structurally harder for the same failure to happen again. Then move on. You don't ask who caused this, you ask what did our system allow to happen, and how do we make it harder for that to happen again? Okay, let's close the loop. Observability is the nervous system of your software. The code is the muscle. The database is the memory. But the metrics, logs, and traces are the nerves that tell the brain when something is wrong, and where, and why. Don't fly blind. Use metrics for vitals, logs for details, traces for the journey. Watch the 4 golden signals: latency, traffic, errors, saturation. They are the pulse of the system. Respect the tail, ignore the average, optimize for P99 because the tail is where users feel the pain. Alert early on saturation. 70% is your ceiling, not 100%. The math past that point is not on your side. Use error budgets. Turn reliability into a business decision, not an emotional one. When you have true observability, you stop guessing. You stop saying, I think the database is slow. You say, the database P99 latency increased by 40 milliseconds because disk I/O hit 85% saturation at 1432 UTC. That is the language of a senior architect. That is what it looks like to not fly blind. In the final video, video 15, we're going to take everything from this series, the B-trees, the consensus algorithms, the distributed caches, the async queues, the observability layer, and design a global scale system from scratch, something like TikTok or Uber, end to end from first principles. See you there.